In this video, I'm going to measure what we need to measure in order to calculate the kinetic energy of rotation and the angular momentum of a spinning CD-ROM. We'll also have to look up something online about how fast CDs spin. Well, I already looked that up, and I found that these things spin anywhere between 500 and 200 RPM. They spin faster when they're reading data on the inside part of the CD and slower when they're reading data on the outside of the CD, so that the computer reads the data at the same linear speed. Now, in order to calculate the kinetic energy of rotation, we're going to need 1/2 I omega squared. So we'll use omega as 500 RPM, but we'll need to calculate that in radians per second. And we're also going to need its moment of inertia. We'll need the moment of inertia too for the angular momentum, because the formula for the angular momentum of a rigid rotating object is I omega. So we need to measure what we need to measure in order to calculate the kinetic energy, the moment of inertia of this thing. Well, I'm sure that you know we're going to need its mass and its dimensions. So here's a quick measurement of the CD's mass, 16 grams. We're also going to need to know how big the CD is. So I'll measure two things. I'll measure across the outside diameter, that's 12 centimeters, and I'll measure the hole, that's 1.5 centimeters. So you better jot those things down. What we have for this CD is its spinning rate is 500 RPMs, revolutions per minute. Its mass, 16 grams, and the inner and outer diameters are 1.5 and 12 centimeters respectively. So what are we going to do with the 500 RPMs? Realize we're going to need to get that into radians per second, because we want to calculate everything in SI units. So we can do that in the usual way. We'll take 500 revolutions per minute. We got to multiply it by a string of factors that'll turn revolutions into radians. Well, that's 1 revolution is 2 pi radians. And we got to get the minutes to seconds, so that's 1 minute, 60 seconds. So if you string those factors along, I think you get 52.4 radians per second. But you better check my math. Now, we did know that the mass of the CD was 16 grams. Its outer diameter was 12 centimeters, and its inner diameter was 1.5 centimeters. We're going to need those and the right formula to calculate moment of inertia. So you have to take a look in table 9.2 to figure out which of the formulas is most appropriate for calculating the moment of inertia of that CD. Well, it's pretty much like a disk, and the formula for the moment of inertia of a uniform disk is 1/2 mr squared, except this has a small hole in it. So it's really more like the cylinder with the hole in it. And I think if you pick the formula that's the best match, you're going to find this. We need to calculate 1/2 m times the outer radius squared plus the inner radius squared. Now, before you start banging away with the numbers that are given, realize that you need the mass in kilograms, and you need all these distances in meters, plus what we measured was the diameter, and in our formula we need the radius. So how about you try to plow these together, not making the rookie mistakes, and see what you get. I already did it, and I get 2.92 times 10 to the minus 5. And the units for moment of inertia are kilogram meter squared. Mass, kilograms, distance squared. Excellent. So on to calculating the kinetic energy of rotation. We need to evaluate the formula 1/2 I omega squared. But again, we got to make sure we got I in SI units, which we do, and we got omega in radians per second, which we do. So you can evaluate this formula and double check that you get 4.01 times 10 to the minus 2 joules. Now, if this were an answer to 2 sig figs, what do we have here? So all of these, 2 sig figs. And this, well, it's really only 1, but it depends. We can make this 3 if we demand that these zeros are actually measured values, But anyways, let's work out a 2 sig fig answer. So if you were asking a question at this point, you would say the kinetic energy of rotation is 4.0 times 10 to the minus 2 joules. Not too much. And if you want the angular momentum of a rigidly rotating object, you need I omega. So that's pretty easy. In fact, that's easier to multiply out. And if you do it, I think you get 1.53 times 10 to the minus 3 kilograms meter squared per second. One last thing I want to tell you about units. The unit radian isn't really a unit. It's a placeholder. If you think back to the way angles are measured, an angle in radians is a ratio, the ratio of an arc length swept out by a radius vector. The arc length would be measured in meters, the radius vector also in meters. So angles expressed in radians actually don't have units. So the unit of radian comes and goes as we wish. We tag it along when we're talking about angles and angular velocities and angular accelerations to remind ourselves that it's an angle. But when you put it into formulas, the radians goes away because it's not really a unit. So oddly enough, there's no derived unit for angular momentum. It's just kilogram meter squared per second. The last thing I want to point out is that since the rotational kinetic energy has got some I omega in there, and L has got some I omega in there, that these two are related by relatively simple formulas that allow you to jump from one to the other. So if you wanted to write these down, they might be useful. The angular momentum expressed in terms of the rotational kinetic energy is that, and the rotational kinetic energy expressed in terms of the angular momentum is that. So you can verify that these two numbers, along with omega and I, are also satisfied. But these might be useful to keep track of to quickly calculate one if you got the other. So there we've calculated the kinetic energy of rotation and the angular momentum of a CD-ROM spinning disk spinning at 500 RPM.